Good. It's going to get harder.
Really?
Yeah. Testing. So yeah, we got a test next week on Tuesday. Got to get the projector going. So you got a few days to straighten things out. The test is going to cover, is it just 1 and 2? I think it might just cover test 1 and 2. You've all seen the test announcement, I hope, and the test covers assignments 1 and 2. So check out the solutions to those. You know, the solutions to the assignments are all going to be in the solutions link on Canvas. So if you go to the home page on Canvas, I did that. There we go. On the right side, there's a link under course resources called Solutions to Homework and Tests. You see that? So, question?
You know what Mr. David's?
I'm sorry?
Mr. David Siegel?
Yeah, did you check it? He might be in his office over there. Last, down the hallway, last door on the left.
Thank you, Mrs. Hall.
Sure, James, good luck. Okay, so already you can find solutions to homework 1 there. If you click on this, you'll find links to all the solutions, but most of them will not be active, but the solutions for assignment 1 are there. And as I mentioned, I only graded 3 problems on assignment 1, and your graded work is over there. You guys who came in late, there's a table there with your homework on there. You can grab that. And so I didn't look at your other ones because it's too overwhelming. I just focused on 3 problems. I might just do that from now on. So you got to check the solutions to see if you had any other mistakes you need to come look at and stuff. And then you're responsible for asking me questions if you still don't understand something. And remember, I got office hours online on Sunday nights. Nobody's checked in on those so far. So Sunday night is going to be the next office hour. You can check up online and get help on any homework problems you're having or anything that you're reviewing for the test. There is a practice test as well, so that is available farther down in the test. And I will hand that out later in the week, so you can look at that, and then the solutions are up there for the practice test as well. So just in case you're curious, this is what the practice test looks like. It has a few problems like that. This is kind of assignment 2 stuff. This is position vectors. This is dot product, right? So yeah, so that's what the test looks like. And that's the practice test. So, and you guys who came in late, your return homework is on the table over there. Any questions before we get started on the homework? Can't go too far into it. Any short questions, because I want to make sure I get the lecture in today. Any short questions on the homework? I'm going to have to close this. It's kind of too noisy. Can't hear anything. And let me get this thing going. Oops, I can't do that. I want to do, this thing is really kind of annoying. What do I do with this giant menu bar? Put it down here maybe. There's just never any good place for something like that. Maybe I can make it shrink. That's better. Yeah, your assignment 2 is due today, so if you got assignment 2, don't forget to turn it in. Okay.
Thanks.
So we're going to have basically 2 lectures this week. Problem session on assignment 3 on Thursday. You'll get the practice test to look at over the weekend. Monday's class will be your last chance for any questions before the test. So you want to study really hard, all the practice tests, all the solutions, any questions you have on anything like that, you can bring up on Monday's class. Then you got the test on Tuesday. Yeah. Page of notes, formulas only. Yeah, but no, no like practice, no solutions to problems. Just formulas and stuff. No. Okay. Yeah, I don't like you to do example problems because I might be selecting problems from the textbook or example problems from the book. So that means you're all on the same page. I don't want someone to say, "Oh yeah, I figured out which one they were going to do." Okay, so yes. All the information's on email I've been sending out. You got that email? Yeah. Yeah, just look at that email. It's all in there. There's no access code. You just go to the link. You have to install like an app or something. Yeah, and then once you do that, you go to that URL and it'll take you right to the conference. Yeah. Yeah, video. You can share your desktop. I can share my desktop. I can show you how to solve stuff. You can have a conversation. Yeah, it's really helpful. Yeah. I think I might actually offer extra credit for people to just sign in once, just so you see that it's not that hard. So you know you can do that. I'll probably do something like that. Well, every time I connect right now, I'm using it. It's that simple. But just do it. It's not hard. Yeah, just follow those instructions. You can do it. It's real easy. There's really nothing to show you because you just go to that link and it will take you there. It will install everything you need. Did you do it?
No.
Did you do it? You installed it, right?
Yeah, install it. It's only on the app.
Yeah. So you went, but you didn't actually connect to the meeting.
I clicked on the app with it. I was trying to put it on the meeting.
So you tried? Did you try to tap in last night?
Yeah.
And you weren't able to succeed, huh? Okay.
Is that like a code?
Well, that was the link. That was the link that I sent you. That is the code. That's like the room number. It's like confer.zoom and yeah. All right, I'll make a video because people are still kind of. It doesn't seem. It's not that explanatory. I had a really nice system that worked really well, but it had a little flakiness to it, so I couldn't use that anymore. Anyway. The other thing I'm going to warn you about is I'm going to start putting multiple choice questions on here, which are selected from the lecture. All these multiple choice questions. Each lecture has like 6 multiple choice questions on it. I'd like you to start paying attention to those and go back and look at those as a review because these are kind of nice conceptual questions and some of them are short computational questions. You're going to start putting those on the exams. And eventually, and maybe this semester, I'm going to probably eventually have a multiple choice final exam, which is going to be a lot of based on those questions and questions like that, because that standardizes everything. And I can really tell, you know, when I'm grading partial credit, I really can't, it's hard to kind of subjectively tell how the class is doing, how to objectively tell what the class is doing. So anyway, so start looking at these things and taking them seriously. So when a particle is in equilibrium, the sum of the forces acting on it equals what? 0, if it's in equilibrium, right? Yeah, there's no net force on it, so it's in equilibrium. For a frictionless pulley and cable, the tensions in the cable T1 and T2 are related as what? You want to close the door, somebody back there? They're kind of noisy. Sorry? D. T1 equals T2 sine theta. Not a bad guess. You guys did pulleys already, right, in physics, didn't you?
Yeah.
What did you learn about them?
That they're supposed to like balance out.
It's the same, right?
Nothing to do
Yeah,
with
T1 equals T2. It's B.
it. Okay.
Yeah. When it's a frictionless pulley. Yeah. Good. So, yeah, so we are going to study this notion of equilibrium. And we're going to get some pulley problems. Pulley problems are kind of cool. And this notion of equilibrium relates to the idea that with a force is like an action of something on something else, and it changes that produces a tendency to change the state of rest or motion that the body is acting on. And you can have force is a vector quantity, and it's also a sliding vector, which is kind of interesting. And what that means by a sliding vector is if you attach like a force to a body and start yanking out of here, or you actually happen to attach it further down here and apply that same yank on it, it's going to have the same effect on that body if you're acting along the line of action of the force. So you can move that force anywhere along the line of action, and it's going to have the same effect on the body. That is called the principle of transmissibility. And we're going to use that a lot when we start calculating moments and things. So it is a vector quantity, it's a sliding vector in that you can actually move it and have the same effect. It has a magnitude and a direction and a line of action. So if the body is at rest, the forces have to balance out. In a very simple case, if you have this little piece of wood or something, and you start tugging on it with 10 pounds and it's at rest, then something else has to be tugging on it 10 pounds in the opposite direction. If you're pushing on it with 10 pounds, something else pushing on it 10 pounds is going to keep it at rest, right? Those two examples are this is equilibrium. There are some interesting, in terms of physics, some interesting forces involved. There are body forces and surface forces. So a body force is where if you have some body here, something, and an example of a body force is something like gravity or electromagnetism. And in this case, you have gravity sort of acts at a distance on all the particles in a body and creates a force moving in a certain direction. So if you broke up all that body into a lot of different pieces, they're experiencing this force at a distance, right? And you can think of each one of these things as a weight. And if you have I pieces in that body, you have a whole bunch of weights. And the gravitational net force is the sum of all those little weights. And so you can model that as a big W. So here's the body, and you could say you can replace that with a solid big W like that. Now I kind of did this a little bit backwards. My order is a little bit off here, but the scenario here is that you have a table. Oops. A table with a book on top of it. So that book, in order to be in equilibrium, is experiencing two forces. One of them is the force of gravity, which is pushing it down, right? And this is modeled by a net weight of that body, right? But what's the other force acting on that that's keeping it from falling down? It's a normal force, right? You got that from physics. The force of the table pushing back on it, right? And that's called a contact force. So surface forces or contact force, the normal force is one of them. And this means the body can be, there's other forces acting on the body. There's a whole bunch of little arrows everywhere the atoms of the table are repelling the atoms of the book, right? And that those are called the normal force, Ni. And so these are surface or contact forces. The sum of all those Ni's can be modeled as a single normal force. And then we can classify various force systems as 2D, in which case all the forces are acting at a single plane, versus 3D. And 3D forces are more general. We're going to look at those later. Basically, chapter 3, we're kind of just looking at all coplanar forces. Okay, questions? And the other thing with coplanar is that they can be collinear. Whoops, they can be collinear, in which case, with a collinear force system, that means like the forces are acting along the same line of action, but maybe equal and opposite. They can be concurrent. Concurrent is where all the forces are acting towards a certain common point. And they can also be parallel. So with parallel forces, they are all going in the same direction. Or they can be neither, and that's the general case we're going to cover in chapter 5. Question?
So the collinear facing the same direction, so collinear even if they're not,
Yeah, if they're collinear and they're all facing the same direction, then the system wouldn't be in equilibrium. It'd be a dynamic problem. These are actually all, these could all potentially be in equilibrium if the forces all balance out. And that's really what we're looking at in statics. They always are going to be in equilibrium. The forces are always going to add up to 0. Questions? Any other questions? You guys know Homer? He used to always say, this is the most boring class in the world because all you're doing is the sum of f equals 0. Here it is. Equilibrium. All points of the body are at rest or have the same constant velocity. And when you're in equilibrium, the sum, am I supposed to write this thing out? I guess I'll write this out. The sum of all the external forces equals 0. These are vectors. The sum of all these vectors has to add up for 0 to be in equilibrium. That is an equilibrium equation. And you can use that to find unknown forces. This is how we actually, we use it in order to find unknown forces, because we're given like certain forces applied to a body. There's going to always be like at least one unknown that we're going to have to determine based on the equilibrium equation to figure out what that is. And it's sort of like solving a crossword puzzle. Sometimes there's more than one unknown force, and you have to use different techniques to find those unknowns. That's what we're basically doing for the whole class. So this is, if in 2 dimensions, this is a system of 2 equations and 2 unknowns. And the equations are the sum of all the fx components have to be 0, and the sum of all the fy components have to be 0. And if you go into 3 dimensions, you can do the sum of all the fz components equals 0. So this is for 2 dimensions, and for 3 dimensions, you got to do all 3. Three equations, 3 unknown. This is really hard to read. Sorry about that. Okay, the other thing we do is, oh, did you all get the handout for the problems? By the printer, there's a hole punch. And if, so you can just grab those and hand them out to anybody else who needs them. You guys didn't get one either, right? You guys get one? Yeah. Can you hand them around? Not everybody, but who, if you need a handout for today, please raise your hand. David, grab another chair, would you? Yeah, don't fix it now. And stop breaking our furniture. So the free body diagram is how we do this, right? You got the free body diagram in physics. I guess it's a broken chair. Thanks, Jonathan. Destructive geniuses here. And the free body diagram is where we draw all the forces acting on the body. So I need everyone's attention up here, you guys. Yeah, forget the chair. Thank you. And the way you do the free body diagram is the first thing you do is you isolate the body from all the surrounding things that are attached to it. And you show all the forces, whether the contact forces, whether they're active forces, whether they're reactive forces, and you identify what those forces actually are. This is the conceptual part of the problem, that if you don't get this, then you're going to be really mystified. The whole problem-solving process is just going to be a real challenge. So in a real engineering problem, you might have something, you know, a real object that's in an environment which has got a lot of stuff situated on it, right? So you've got a wheelbarrow where you've got somebody who's holding it, you've got a load on it, a bunch of logs and everything, right? So we have to kind of draw this thing and represent the forces schematically and what's going on here, right? So what we do is we isolate the body. So what is the body that we're going to isolate here? What is the thing that all the forces are acting on? The wheelbarrow, the whole thing, right? So we isolate that body as one big thing. And it's like a rigid body. It's stiff. It's not going to bend or anything unless you really overload it, right? So what are the forces acting on that wheelbarrow? There's like 4. Can you name them? The weight of the load, right? So whatever that load is, it's going to have a weight applied somewhere in its center of gravity. We could call that W1. What other forces are acting on that wheel? Gravity. What about gravity? Isn't that what weight is? The weight of the load? Sorry? Is gravity different than the weight of the load? How so? Yeah, but isn't weight, yeah, weight is if it's in a SI system, weight is mass times G, right? That is the force of gravity, right? So weight is the force of gravity. Right, so if this whole thing has a mass of m1, then the weight is m1 times g. That's the force of gravity of the load, right? Okay, that's one force. What other forces are there? The hand, right? So we have an F sub h pulling up on it, but there's 2 hands. Well, we can sort of simplify it a little bit and just say, you know, well, there's an FH there pulling up on those handles, right? Each hand is going to have F over 2, right? Okay. Yeah. Well, here we're drawing one FH. We're going to combine them together. It's a 2-dimensional problem, so we're lumping both hands into one FH. Yeah. Yeah, good question. What else is acting on this thing? Normal force, right at the bottom where the wheel is. Okay. And of course, there's two wheels, so each wheel would have n/2. But we're simplifying things. It's a two-dimensional problem, right? What else is acting? There's another force. The what? The weight? Sorry? Friction of the ground? Nope. If it's not moving, well, if it's just standing, friction on the handle. No, there's another force. I'll give it to you. Well, the wheelbarrow itself has a certain mass, right? So it's going to have a weight acting on it as well. And we could call that W2. So weights and normal forces kind of balance out in equilibrium. Whatever the weight is of a body, the normal force is going to be, if it's in equilibrium, right, it's going to have an equal and opposite force pushing it up. So for the cylinder, it's going to look something like that. Interestingly enough, so weights are applied at the center of mass, right? This is like the center of gravity. You've heard of that, the center of mass. And sometimes the center of gravity may be off the body, like on this C clamp or the C beam here. The center of mass of that thing is in space, but that happens to be where the normal force is going to be lined up as well. It's going to be right underneath the center of mass. Okay, if you have multiple bodies, you're going to have to break them apart. This is where it becomes kind of like a crossword puzzle. You got to solve one part so you can kind of work your solution through the other part of the problem. Here you have two books on a table or something. The top book is going to be pretty easy. It's just going to have a weight and a normal force below it pushing up on it. The middle book is the more interesting one because it's got a normal force coming below and a normal force above, which is the opposite of this guy, right? This is the same thing as that. And then its own weight followed by a normal force pushing it up from the bottom. So that's how you sort of diagnose this. More complicated situations involving friction, we're not going to get until chapter 8 with friction. That's quite a bit into the class. But when you start doing things like that, you can also break these things down. Again, the top book has a pretty clear breakdown where you now have a normal force, which is always perpendicular to the surface of contact. And then you've got this friction force, which is resisting the motion of that thing down the hill. And if you got a cable there, you're going to have an FC on this guy, plus its own weight here, plus a normal force from above, and a friction force as well of that thing pushing down, and then a normal force there. Maybe if it's a smooth surface, there's no friction on the bottom. You can see each one of those is an unknown, though, and eventually we'll have to figure out ways of solving all those things, given some information like the mass of the books or something, and the friction coefficient. But all those things can be determined given enough information. Yep.
So an example of the slope.
Yep.
It's an equilibrium that stays there, but it's not equilibrium if it fell.
Yeah, it's an equilibrium as long as it's not moving. If it starts moving, then it's actually, if it's moving, I mean, in general, a body that's at motion, constant velocity is also in equilibrium. Yeah. It's only when there's an acceleration that there has to be an imbalance of forces. And we are always pretty much looking at bodies at rest. So, yeah. We also have cables that we're going to get to look at. Cables have tension in them, and the tension is always oriented along the line of the cable. So whatever geometry you've got the cable in, that's going to determine the direction of the force inside the cable. Cable's always acting, the force is always acting along the line of that cable. So you can break it up. The bucket itself has a tension pulling up on it from the cable and a weight trying to push it down. The cable itself is feeling tension in both directions. Again, equal and opposite, so they're all in equilibrium, the whole thing. You've got, girders hoisted up on these things. Again, you can kind of break this down. You've got the mass of that thing. You've got two cables on it. This whole thing, these three forces have to add up to 0, right? and each of these cables, these forces have to add up to 0. At the point where they're coming together at this I thing, then all these 3 forces have to add up to 0 as well. So at each point in that system, you can break it apart and solve for the systems of equations of equilibrium. And then there's springs, another thing you learned in physics. In springs, you've got an equilibrium length of a spring where it just wants to stay at that one particular length. And that is, the equilibrium length is called L0 of the spring. And if you stretch it, you're going to get some additional displacement S. And the spring constant tells you that the force required to get a displacement S is going to be some constant times the displacement that you're looking for. That's the spring constant. It's linear. And this S is just L, the new L minus the original unstretched L. So if you've got a mass on that spring, pulling it down, then the mass is going to experience, in equilibrium, it's going to experience the force of the spring pulling it up and the weight of gravity pulling it down. The spring itself experiences the force Fs pulling it down as well. Springs can also be in compression. It works the same way. Again, if you've reached equilibrium with this block on top of the spring, then the spring force has to balance out the weight of the mass. And sometimes you're asked to figure out, well, what's the displacement given the spring coefficient is this, that kind of thing. Finally, again, we're going to look at pulleys in this class, and pulleys in equilibrium are pretty interesting. Here's a complicated system, and if you're interested in what's happening with a pulley, you can diagram that pulley, and with a smooth or frictionless pulley, you can convince yourself pretty easily that T1 has to equal T2. We're going to be looking at cases. Our book actually covers cases of non-frictionless pulleys. Those are more complicated. But that's sort of the rundown of all the kinds of forces in general that we're going to be looking at. And now we have a practice problem, right? Is this on your handout? Yeah. So the practice is the sphere has a weight of 60 newtons. Draw the free body diagram of the sphere, the cord, the knot, and the pulley. Again, this is an analytical process. You're breaking up a complicated system into smaller pieces so that you can actually determine what all the components are. You can then solve components throughout the system until you solve the whole thing. We don't have to solve for the forces right now. We're just asked to draw the free body diagram. So we can start with that sphere. Put that over there. The cord, CE, again, we're kind of exploding this system. So here is your cord. So the sphere has a little loop on it, E. So this is your cord, CE. There is a knot at C. You can kind of draw a little figure 8 or something. That's the knot. And you can draw all the forces acting on that. And then there's a pulley at B. And the pulley just removed from everything else. Just a pulley floating in space at B. Okay, we're going to go through and just sort of figure out what are the forces are acting on each of those pieces. We've exploded that thing. We don't have to worry about the spring, but that will contribute a force to the system. Let's start with the sphere. What are the forces acting on the sphere? Gravity. Pardon me? The mass of the sphere. What is the mass of the sphere? $60? Yeah. What's that? 60 divided by G is the mass, right? Good. Yeah, so the mass is 60 divided by G. So 60 newtons is the weight, right? So if you want to know the mass, you take 60 newtons divided by g. It's like 6 point something, right? Kilograms. Yeah, kilograms, good. So you can draw this weight going down. Okay, and if it's in equilibrium, what's going to be happening else to that thing? So normal forces are generally contact forces for like surfaces. So we usually don't call it a normal force. But what other force is acting on there? A tension force from the cable CE, right? We could draw that as an arrow going up. That force is pulling it up. And we got to label it. You know, we know it's 60, but let's make a variable for it. This is a tension force. You could call it TCE or FCE because it's related to the cable CE, right? Right. What's acting? So that's it. Are there any other forces on the sphere? Nothing, right? Just two forces. Those have to add up to 0, right? What about the cable? What's acting on the cable? Tension. Where? Okay. How do I draw it? At E, it's going down, right? Again, if you want to call these tension forces, that's totally fine with me. Let's call this TCE. Then you're going to have TCE here, right? You're going to have TCE here. Cable's feeling a stretch. Okay, what about the knot at C? What's it going to be feeling? There's a force, I'm sorry? The force acting down, we're going to call what? TCE, right? It's the same unknown. And there's a force acting to the side, is that what we're saying? From the spring, right? So it's, which way is it pulling it? Right, what do you want to call it? TCD is not a bad guess. That's sort of you usually use tension forces for cables. So F sub S for the force of the spring is kind of reasonable. And what else? But if you want to call it FCD, that's fine too, or TCD. It's not going to kill you. What else? Matthew?
The pulley force that's at the angle there. On BC.
On BC. It's acting on the knot, right?
Yeah.
So what are we going to call that?
Oh, that's BC.
FBC or TCD, either one, or TCB, right?
Yeah.
And the angle of that is 60 degrees, right?
Why is the arrow pointing up?
Why is the arrow pointing up? Whoops. Why is the TCB arrow pointing up? Okay, good. Because from the point of view of the knot, this is the point, and actually this is maybe can kind of be confusing sometimes, right? Because the knot is pulling that pulley down, right? But from the point of view of the knot, what's it experiencing? It's experiencing this force trying to pull it, right? So that's what we're doing. For each subcomponent, we're thinking, what is it feeling? What does it feel like to be that knot? It feels like you're being pulled in 3 directions, right? You're being pulled down, you're being pulled to the right, and you're being pulled up and to the left. David?
I thought it was divided that down to simplify an object into a single point.
You thought with free body diagrams, you simplify an object to a single point.
Right.
And that is true for a lot of simple problems. And in in solving this particular problem, there is one point that kind of has all the stuff going on at it. What point is that? It has all the sort of important point forces. Sorry? The knot. Yeah, you would pick that knot and just do the free body diagram of that knot. For today, we're just kind of exploring what free body diagrams can do for us. We're exploring the free body diagram for every little piece on the system. Because eventually you're going to have systems that actually have multiple points you got to look at. So you got to actually look at this point here and, you know, solve it here, and then you can take some information here and move it over here and then solve it to that system.
So like in the spirit of thinking about the anchor.
Yeah, and the sphere, you know, it's trivial, right? The sphere is trivial, the cable's trivial. The only really interesting point is the pulley, I mean the knot, and the pulley is kind of interesting as well, but it can be sort of just subsumed in the knot, because once you get the tension from the knot, it's the tension on the cable, of the pulley. Sorry, anyway. But let's just look at the pulley. We're using the free body diagram as a way of inspecting, you know, the inner workings of a system of forces and stuff, right? And you can explore other parts of the system beyond the part of interest that you're going to use to solve the problem, because it applies everywhere, right? The free body diagram is like a universal way of looking at stuff, looking at forces inside things, inside structures, inside systems. So let's look at the pulley. What kind of, if you're the pulley, what are you going to be experiencing? The tension from what? Yeah, the cable. In fact, that pulley just has one force, you know, acting on it. You can call it TBC again, right? And the force is pulling it this way, right? It's equal and opposite of what the knot's feeling, right? And then also there's this force, and this is, again, 60 degrees here. And then there is another force acting, oops, that's a 45-degree angle. Let me draw a little more shallow. Acting that way, pulling it that way, right? And so what's keeping that pulley from actually falling down? With these two forces acting on the pulley, it's going to go straight. It's going to go down, maybe down and to the left or down and to the right. There's something else that's keeping that in equilibrium. What's that? Yeah, the bracket or whatever that thing is, right? Acting through the pin of that pulley is doing what? Which direction is it? Notice that thing is on like a swivel. That looks like a swivel, doesn't it? So you can imagine that the force that the pulley is feeling is in which direction? Up and probably up and to the left, kind of along the line of that swivel, right? So it's going to probably be going something like this. And it's acting kind of through the pin of the axle of that pulley, right? Like that. And you could call this like just FB or something. It's not really a tension, but it's something acting on the pulley. It has some angle. Now, you don't really know what the question is, right? The question might be the sphere's weight of 60 newtons, you know, what are all the forces acting on the knot? The question could also be, you know, the sphere is 60 newtons. What is the force acting on the pulley from that little linkage there, right? It might be asking you, what is FB? In that case, you do have to diagram the system. You got to explode it. You got to do the knot first. You can solve all the forces of the knot, and then you can take those forces and figure out what FB is. But you can't solve FB directly because it's too buried in the system. Does that make sense? So it's kind of a spirit of exploration when we kind of look at these things. Here's another example. We've got a 10-kilogram sphere at rest, and we want to determine the normal force on the floor and the tension in the cable if there's a horizontal force of 20 newtons pulling it to the right. Typically, we are going to say something like, well, we need to find N and T, the normal force, and the tension on the cable. That's what we're asked to find, right? And we're given that F equals 20 newtons, and the weight is M times G, which is 98 newtons. because M is 10 kilograms. And again, we would start with a free body diagram, right? We would figure out what that sphere is actually experiencing. Well, we know there's a weight. We figured out what the weight already is. The weight is 98 newtons. We know that there is a force pulling it to the right. There is a, well, what other forces are acting on that thing? Tension force pulling it up and to the left at 30 degrees. Ah, what did I do? There are too many like danger zones when I'm using this stuff. Yeah, so it is up and to the left. So this is 30 degrees, and this is a force, say, T. We're going to have to figure out what that T is. Oh, there's also a normal force, right? Now, in order to solve this, we find, okay, at rest, you know, we're in equilibrium. And we're going to have to find that the sum of all those vector forces equals 0, right? And because it is a single point, single particle system, it's really just one vector equation. Sum of all those forces equals 0. It is a 2D problem, though, and that means you're going to get two scalar equations. And they're going to look something like this. The sum of the fx's is going to equal 0. And all we got to do is tally up what those x components of those forces are. The sum of the fx's are going to be, what are all the horizontal forces acting on that sphere? Well, you got F, right? What else do you got that's horizontal? T, but it's not completely horizontal, right? T is tilted at a 30-degree angle. So what is the horizontal component of T? Yeah, T cosine of 30, right? So we're going to say, and it's pointing in the negative x direction, right? So minus T cosine of 30. And that has to equal 0. And that means that T is going to equal F, which is 20 newtons, over the cosine of 30 degrees, which is going to equal 23.1 newtons. That's a nice one because you can solve that. There's only really one unknown in that equation. And then the second equation is that the sum of the Fy's equals 0. What are all the horizontal, the vertical forces? You got the weight, you got the normal force, so you got N, minus W, right? W is going down. And then what else you got? T sine of 30, the vertical part of that T, right? So plus T sine 30. And that means N plus, I'm sorry, N minus 98, whoops. Plus the 23.1, which is T times the sine of 30, has to equal 0. That means your N is going to equal 86.5 newtons. So we just solved these two unknown forces. That's pretty good. If you needed to know, like, how strong of a cable are you going to need for that thing to not break? You know, well, it has, that cable has to support 23.1 newtons. How much load can that floor, does the floor need to be able to handle to support that sphere? Well, it has to be able to handle 86.5 newtons. These are all useful things when we're actually working on real systems, right? I'm trying to design something. Yep.
So because it's an equilibrium, you said it would be 0.
Yeah, because it's an equilibrium, everything equals 0. All the forces have to have. Pardon me? Well, there are actually two unknowns in that problem. The normal force and the tension in the cable. It just turned out that you could solve them individually in each equation. Some equations are going to have two unknowns in both equations. You got to solve using matrix stuff, right? Yeah. Good. Here's another example. We're going to skip this because of time. But again, in a similar way to the knot thing, you focus on a particular part and you solve that. You know what sac A weighs, so this knot at E is kind of where you could start. And then once you know what's going on there, then you can figure out, what is this weight of sac B, because this has to be in equilibrium with all that information there. And anyway, too much information. Let's get a concept quiz along the way here. Assuming you know the geometry of the ropes, you cannot determine the forces in the cables in which system above. What's the force in these cables? 500 each, right? What's the force in these? Well, the angle is going to affect it, right? The vertical part has to be 500 from each side, right? But you can solve that. When you got 4 cables here, that's kind of a stupid question. I don't like this one. Yeah, it's C. Assuming you know the geometry of the ropes, you cannot determine the forces in the cables in which system above. The point is, this one has too many unknowns, I think. So, yeah, that's kind of a dumb question. Too many unknowns. That would be C. But I think that's actually wrong. I think this is a wrong question, but anyway. Let's look at one more. Let's see how this attention question goes. This is good. Select the correct free body diagram of particle A. Sorry, let me move this thing out of the way here. D. Right? Everybody agree? D. Yep. There's one more. Using this free body diagram of point C, the sum of forces in the x direction of sum of xx is. Which equation is right? B, right? F2 cosine of 50 is positive. That's the horizontal part of F2. You got 20 going in the negative. Equals 0. B. Good. Yeah, so these are going to be on the I'm going to put some multiple choice questions like these on the test. So, ooh. Yeah. That means we have to cover them in each lecture. So.
The last problem.
Pardon me?
I'll go through in the last
Oh, okay. Do you want to staple it to the rest of it?
Yeah.